Assalamu alaikum. Welcome to today's physics teleclass. Today's session will be taken by myself Ibrahim Muzar
and myself Sunil Kumar.
In today's lesson, the first part will be taken by me and Sunil sir will take over the second part of the lesson. Before we start, we will first look into the objectives of today's lesson. So, by the end of today's lesson, you should be able to use the term half-life in simple calculations, calculate half-life from data or decay curves, describe the structure of atom in terms of positive nucleus and negative electrons, and describe how scattering of alpha particles by a thin metal foils. So, before we proceed further, let us recall what we have learned about atoms. As you can see, the atom consists of three types of particles, which is protons, neutrons, and electrons. As we all know, the neutrons and protons are inside the nucleus and electrons are orbiting around the atom, the nucleus of the atom. In some cases, some of the atoms, which we call as isotopes, sometimes they have more number of neutrons or less number of neutrons, so basically varying number of neutrons. Due to this, some of the atoms become unstable. Due to this instability, to become stable, as we all know, as we have studied in the previous lesson, the atom tries to become stable by becoming radioactive. In this process, they will be either emitting alpha, beta, or gamma. But what we must note is that we don't know what type of particle it is going to emit, because we call this process a random process. As I've mentioned, that when a radioactive nuclei, when it undergoes radiation, we don't know what kind of an atom or what kind of a radioactive particle it will emit. As I've mentioned earlier, when a radioactive nuclei undergo radioactivity, it will either emit alpha, beta, or gamma. But since we've called this process a random process, we don't know what kind of radiation it will emit and when the process will take place. In a case where we have a single nuclei, we will not be able to identify things easily. But in a case where we have a lot of radioactive nuclei, what we need to understand is we can identify two things. Number one, that is the activity. So, how do we define the activity? It is the overall rate of decay of all isotopes in the sample. Now, you must be wondering what decay means. So, we have discussed that in our previous lesson, that when a radioactive nuclei undergoes radioactivity, that is called a decay process. So, if it is emitting alpha, beta, or gamma, that is called decaying. And the unit of activity is in becquerel. And the other thing that we know from the radioactive process is the half-life. You must be wondering how to define half-life. We can define half-life in two ways, in terms of the number of radioactive nuclei and in terms of the time taken for the decay of the activity or the activity to reduce to half of its initial value. Now, in simple terms, when we talk about the activity, that can be explained as the number of disintegrations taking place in a second. Or maybe you can define it as the number of radiations that are emitted in a second. So, we will express the radioactivity in terms of activity. Now, when we define half-life, it is either you can define it as in terms of the time taken for the activity to reduce to half of its initial value. Let us say, for example, the initial activity of a radioactive sample was 2000. The radioactivity will reduce by 2900, 2800, 1500, 1400, and then it will reduce to 1000. As you can see, half of 2000 is 1000. So, which means the time taken for the initial activity to reduce to half of the initial value, that duration, that time period is what we call as half-life. In other terms, the time taken for the number of radioactive nuclei to half from its initial value. Let us say, for example, the initial nuclei, we have 1 million radioactive nucleus. The time taken for 1 million radioactive nucleus to reduce to 500,000, the time period between those is called the half-life. As you can see from this diagram, the green and blue colored particles are the radioactive nucleus, and the ones that are becoming red, those are the decaying particles. As you can see, as the radioactive process continues, the number of unstable particles decreases. So which means the overall rate of decay, which is the activity, also decreases. So as we have described earlier, the half-life in terms of the radioactive nuclei and the half-life in terms of the activity of that, it can be completely correlated. Now, this radioactive process can be presented in a decay curve. So in a decay curve, you have activity against time graph, and as you can see, it is an exponential graph. So gradually with time, the amount of activity of a radioactive sample keeps on reducing and reducing. And as you can see from this diagram, the initial count rate was at 600. What you need to understand is at half-life, it should be reduced to 300. The time taken for the activity to reduce from 600 to 300 was 2 hours. Let's say, for example, the time taken for the activity to reduce from 300 to 150 is still, as you can see, 2 hours. So from this graph, we can deduce that the half-life of this radioactive sample is 2 hours. Now, when we look into this diagram, the radioactive process is quite faster than the previous one. So as you can see, the graph, the exponential graph, it moves a bit faster. As you can see, the initial rate was 2000. So the time taken for it to reduce to 1000 was 1 hour. As you can see, you have to be very cautious about the time, the unit the time is given. It could be in terms of hours, it could be minutes, it could be seconds, it could be days. The next part will be taken over by Sunil sir.
Now we can check some questions relating half-life. Okay. Now you can see one question here. A reading is taken every 10 minutes of the number of emissions per second from a radioactive source. The table shows the reading. What is the half-life of the source? So we want to find the half-life. Some informations are given in the table, and time per minute and number of emissions per second given. And I think all of you remember the half-life, the definition of half-life. Then now we can check. First, number of emissions per second. First, it is 800. 800 emissions is going on first. Then we have to check half-life. Half-life means time taken to decay half of the number of emissions. Now, half of 800 is how much? We have to think half of 800 is how much? Now we know 800, half of 800 is 400. So I'm writing like this, 400. Okay. To reach 800 to 400, how much time taken? We can check. To reach 800 to 400, how much time taken? From this question or from this informations, you will get 800 to 400, 20 minutes taken. So half-life, I can write here 20 minutes. Again, one more time we can check. Half of 400 is how much? Half of 400 is 200. Okay. Then again we can check. 400 to 200, how much time taken? 400 to 200, 40 minus 20, so again 20 minutes. Now we got the answer. Half-life, what is the half-life of the source? We got the half-life. Half-life is 20 minutes. Here, second question. One graph is given, and you can check the question. The graph shows how the decay rate of radioactive source changes with time. And decay rate is plotted here, time per days it is plotted. And question is, what will be the decay rate at 8 days? 8 days, after 8 days, what will be the decay rate? That we have to find. Now, what will be the decay rate in the beginning? Beginning from the graph we can understand decay rate is 4000. 4000. Then half of 4000 is how much? Half of 4000 is 2000. So we can check how much time taken to reach 2000. You can check from this graph 4000 to 2000 how much time taken. 2 days taken. Look, 4000 to 2000, 2 days taken. So half-life is 2 days. Now the question is, after 8 days, how much is the decay rate? So we can check again 2000 to 1000, that means half of that one. 2000 to 1000, how much days will take? Again 2 more days. Again 2 more days. So now 4000 to 1000, total 4 days over. Question is after 8 days. Okay, again we can check 1000 to 500, that is half of that one. Again half-life is 2 days, so 2 more days. Half of 500 is 250, so again 2 more days taken. Now we can check after 8 days, 2 plus 2 plus 2 plus 2. That means after 8 days, how much is the decay rate? So we got the answer, after 8 days it will reach 4000 to 250. So we got the answer 250. Okay, then next question. A radioactive source produce a count rate on a detector of 1600 counts per second. After 32 hours, the count rate has fallen to 100 counts per second. Both count rates have been corrected for background radiation. That means background radiation we detected. Then what is the half-life of the source? So in this question we want to find the half-life. They given 1600 counts per second in the beginning, and finally it is 100 counts per second. Total time taken, it is given 32 hours. So from this information we have to find the half-life of the source. So again we can start. First count rate is 1600, and half of that one 800. To reach 800, one half-life, but we don't know the half-life, we want to find finally. Then again half of 800 is 400, so one more half-life over. Then again half of 400 is 200, again 100. So 1600 counts per second to 100 counts per second. Now total time taken, total time is 32 hours. 32 hours. What will be the half-life? That is the question. So from this information we know 1600 to 100 to reach 32 hours taken, 32 hours taken. So what will be the half-life? Now we can check 1, 2, 3, 4. So we can find the answer 32 divided by 4, so 8 hours. So 8 hours is the half-life. Now we can check, look, 8 plus 8 plus 8 plus 8, total 32. Now we can go to the next part of the lesson. It's alpha particle scattering experiment. Rutherford alpha scattering experiment. Now lot of experiments conducted by the scientists to discover the structure of atoms. And first J.J. Thomson introduced a plum pudding model, and after that 1911 British physicist Ernest Rutherford conducted one experiment using alpha particle. And first, why he selected alpha particle? Because alpha particles have high energy and heavier. That's why he selected alpha particle. And a lead box containing an alpha particle he taken, and here gold foil taken, and this one is fluorescent screen. And why he selected gold foil? First he took a lead box containing an alpha source. Okay, alpha source is there and a small slit is there, through that alpha radiations can go outside. And after that, one gold foil. Why he selected gold foil? Because gold foil contain a small thin gold foil contain more than 1000 atoms. Okay, then next one is fluorescent screen. Fluorescent screen. And we know when an alpha particle hits the fluorescent screen glows light. Now he conducted this experiment and he got 3 different observations. Okay, then most of the alpha rays non-deflected and some alpha particle deflected and some rebounded or rebounds. And actually he expected all the alpha rays undeflected, or all the alpha rays will pass straight through the gold foil. But he got different observation, and most of the alpha particles undeflected and some deflected and some very few rebounded. Most of the alpha particle undeflected. Okay, from that he concluded one thing: most of the space in an atom is empty. That's why most of the alpha particle is going straight, and some alpha particles deflected. From that he understood the nucleus, that means positively charged part in an atom, that is very small. Okay, nucleus contain positively charged, nucleus having positive charge, so some alpha rays are deflected because alpha have positive charge, positive and positive repel. And third one, some alpha particle, very few alpha particle is rebounded. That means the nucleus, the positively charged area in the nucleus, in an atom, it is heavier. Okay, nucleus is dense or heavier. That's why some alpha particle is rebounded. And most of the alpha rays are non-deflected. That means atom consists mainly of empty space. That means most of the area in an atom is empty. Then the atom contains positive charged nucleus. That's why some alpha particles are deflected. And atom contains small dense nucleus. The nucleus is heavier or dense. That's why very few atoms, very few alpha particle rebounds or rebounded. Understand? And one more thing, the nucleus is very, very small. How he can understand? No? If lot of particle, if the nucleus is large, then lot of alpha particle has to be rebounded. But here very few alpha particle only rebounded. That means nucleus is very, very small. And these are the conclusions. First one, an atom contains lot of empty spaces, and second one, nucleus having positive charge, and third one, nucleus is dense or heavier. We study a lot of things today relating half-life and calculation and alpha scattering experiment. And we can check what are the things. Use the term half-life in simple calculations. We study half-life term, definition of half-life, and also calculations. Then how we know how the half-life calculation can do from the decay curve. Then structure of atom. Atom contain positively charged nucleus and electrons are revolving around the nucleus. Then and also alpha scattering experiment, Rutherford alpha scattering experiment. These are the references.
So that concludes today's Teleclass on physics. So thank you for watching the class and see you in the next class, inshallah. Thank you
Okay,
and
thank you.
wassalamu alaikum.